Good morning, students. So this is our lesson we're taking from home because of the severe weather warning. Just loving to see all this rain outside. um, anyway, so let's continue our discussion from last time. So we were talking about the universe. We talked about how our universe keeps getting bigger as our model changes. We've got planets in a solar system, and then the solar systems are orbiting in galaxies, and the galaxies cluster together. Oh, here's more galaxies. We can see these. These are actually pictures of galaxies. Look at them. Some of them are actually really pretty. And then they cluster together to make a universe. And these clusters and these lines of galaxies that are all gravitationally bound to each other, it's constantly expanding. And this goes back to the expansion of the universe, goes all the way back to the Big Bang when everything was close together, and it's been slowly spreading out since then. I say slowly, it's been going pretty fast, but it's just covering massive distances, so it takes a long time to fill it up. Okay, today I want to talk about galaxies. Okay, this is our discussion for today. If you've got your guided notes, you'll see that we have 4 different types of galaxies we're going to talk about in our notes today. So let's just jump in. So a galaxy, as you know, we've got tons and tons of stars and solar systems orbiting around the central point. The central point is not a large sun. It is actually just a cluster of stars. They're just much more densely packed, and it makes it very bright in the middle and then darker as you get out, as you get farther out on the galaxy. And even though this looks like a dark cloud, those are just dimmer stars. And so they just aren't as bright as the middle. That's something to keep in mind. Every single pixel here, and this is kind of a grainy picture, so it's not the best one, but every single pixel here, every single dot is a star. Some of them are brighter than others, but they're all stars. Okay, you can't see anything else from this far away. If it's not producing light, you just won't see it. Okay, so, my face is over my picture of Isaac Newton. Let me move my face up here. Okay, so this all goes back to Isaac Newton, his universal law of gravity. And everybody knew about gravity. It's not like gravity was a new thing. But he's the one who, he gave it a name. He gave it some rules to define how it works. Everything falls. Here's the famous apple. By the way, they tell you in school that the apple landed on his head. It didn't. It just hit the ground, and he thought about it. It maybe didn't even fall. In his journal, he just writes about looking at an apple and knowing that it would fall. But he looked at that and he said, well, gravity makes things fall. So if gravity is going to make things fall, why doesn't the moon fall to the earth? And so he was the first one to say, maybe everything is pulled by gravity. The planets, the moon, everything out in space, everything is pulled by gravity. This was pretty radical for his time, because they still hadn't adopted the idea of the heliocentric, where the sun is in the middle of the solar system. And so there was some controversy over this idea, but by demonstrating mathematically that it could work, he was able to allow universal gravity to be accepted more widespread. So basically what he was saying is, because the moon is in orbit, it doesn't fall. It is actually falling to the earth. It just keeps missing, and so it goes in a perpetual circle. But think about it. Objects like to go in straight lines. An object in motion stays in motion. So why does the moon stay in a circle going around the earth? Why doesn't it float away? And that's because gravity is keeping the moon in, but because the moon's moving so fast, it never falls and crashes into the earth. Here's this equation. You don't really need to know it. What's important, though, is this is mass 1 and mass 2, so we've got 2 objects. The more massive they are, the stronger the force of gravity is. R is the radius, or the distance they are apart. So the farther apart they are, this is in the denominator, so the weaker the force is. So big objects close together have a strong gravity, but the farther apart they are, the weaker the gravity gets, and the smaller the mass is, the weaker the gravity gets. That's all you really need to know. And so he created this design. He drew this in his journal, and he talks about how is it that if an object's moving fast, it stays in orbit. That was the kind of the big question, is why doesn't the moon fall even if gravity is holding on to it? So we're going to go, not yet. Where did I put it? Newton's canon. So this is Newton's canon. This is his journal, and we're putting an animation to it. So imagine that there's a cannon on the top of this mountain, and it's going to, let's turn the sound effects for fun. It's going to shoot a cannonball at 500 meters per second. That's pretty fast. Okay, it shoots it, and this is the whole world. So even though it's going pretty fast, to our perspective, it looks like it barely goes anywhere and it falls. Okay, let's increase that up to 1,000. It goes a little further. Let's increase that up to 2,000. 2,000. 21. That's fine. Okay, and you're starting to notice it follows a parabolic arc as it falls to the ground. But it says, Isaac Newton said, well, if it got going fast enough, as it falls, the Earth will start to curve away from it. So it actually could go a little bit farther than it normally would. If the Earth was flat, this one would have hit a little bit sooner. That's still not good enough. Let's go up to 443 is good. And you see, after a while, if it gets going fast enough, it actually falls into that curve a little bit more. I don't know if that makes sense. Let's do a little bit faster. And if it gets going fast enough, it starts to actually follow the curve a little bit, and so it doesn't hit right away. It follows the curve around. Let's go. And you could even get it to follow the curve all the way to land on the other side of the Earth. And if I think it's 71, 72 maybe. Eventually, it just never falls, because as it falls, the Earth starts to curve away. And so it just forever just goes in a circle until it goes all the way around and hits the person shooting it. And if you shoot it fast enough, it actually, instead of falling, will actually go away from the Earth. And then, where'd it go? And then it will fall back down. Okay, so hopefully this kind of explains it. This is not a physics class. You don't need to understand orbital dynamics super well. But the point is, things, if they're moving, if they're just sitting still, they fall straight to the Earth. But if they're moving, they can actually fall in a circle and never actually fall into the middle of the planet. They can just do circles around the planet. This is why the International Space Station, where the astronauts live, it circles the Earth. I think it's every 3 or 4 hours it circles the Earth. Okay, it has to be going very fast to stay in orbit. And satellites, they're flying, they're going way fast. If you don't make them moving fast enough, they fall back to the Earth. Okay, let's go back to the slideshow. I gotta move my head so I can push the button. Present. So there's a video that kind of demonstrates it, not perfectly, but hopefully you've seen these before.
This is the way the world works normally.
I don't like him talking. Okay, and they just go in circles. These pennies, do you see that? How the pennies are just going in circles? Now eventually the pennies go down into the middle, and that's because friction is slowing them down, and as they slow down, they start falling inward. But you can imagine if these were planets in space, there is no friction, so there's nothing slowing them down, so there's no reason why the planets would go to the middle. But they just keep doing circles around the outside. There it is, doing a circle. Okay, so this is a really good visual to show how gravity actually pulls in planets and keeps them moving in a circle, as opposed to just pulling them straight in. Alright, and I'll let you deal with this more when you get to your physics class. They'll talk more about orbital dynamics and Kepler's laws. Or if you take astronomy we'll talk about it too. But that's the general idea I want you to have in your head. They're doing circles. They are getting pulled in, but they're just doing small circles, and if they slow down, they'll spiral in and eventually crash. Next slide. So after the Big Bang, we get these giant clouds of gas, and it's mostly helium. Helium is the lightest element. It's just got 1 proton and 1 electron. Hydrogen. Helium has 2 protons and 2 electrons. So we get these big gas clouds. And these gas clouds are big, so they have a lot of gravity, but they're also spread out really far, so that gravity doesn't really have a chance to do much. They wander through space and they bounce off each other sometimes. And these clouds look really dense, but they're actually not. You might only get 4 or 5 helium atoms per cubic meter. So, for space this big, you've only got a few atoms compared to on Earth, where you'll have billions and billions and billions of atoms. So that's something to keep in mind. They are pretty spread out, and these images are very hard to take. You can't just put your camera and take a picture of it. You've got to do a really long exposure to see these gas clouds. But we're starting to get these gas clouds in our images. We can start to see them. This is how the whole galaxy, the whole universe started out. It's just these clouds. And slowly gravity starts pulling them in together. And as they start falling into each other, some of them will just collide and they hit and they get stuck together. Some of them are moving fast enough that they actually start doing circles around the center of mass. So this is an animation. We can't see this happening, This process takes so long that by the time we could film it or record it in any way, there's nothing to, like, our lifetime is so short that this thing barely changes. From the day you're born until the day you die, this barely changes. So we do computer simulations to try to see if we can make the spiral galaxy shapes, to see if our models are correct, because we can't watch this happen. We have to kind of guess and make mathematical models. So here's the model that we have. Starts off as a big gas cloud, and already you start to see little white dots where the gas clouds are starting to gather together, and they're forming stars, and that's why they're getting brighter. And the whole gas cloud is starting to compress. And these are actually galaxies. So we're looking at this at a big scale. These are galaxies forming. So I mean, there's a ton of stuff in this gas cloud. And this computer is actually simulating a lot of different information all at once, and which is why we need computers to do this. We can't do this by hand. But you're starting to see they cluster together, and the smaller galaxies join together to make bigger galaxies. Some stuff gets thrown out into space when that happens, but slowly we start getting bigger and bigger galaxies forming as all this gas cloud comes together into one chunk. And here's a collision. And we say collision, but we're thinking of like solid objects crashing into each other. But remember, these things are mostly empty space. So we're not actually getting solid objects crashing into each other like if you threw your toys at each other or something. These are mostly empty space. They can actually galaxies can pass right through each other. It's just the gravity that starts messing them up. They pass through each other and are affected by each other's gravity. So we think we've got a pretty good idea of how galaxies form. Because the computer simulations make galaxies, we think we've got a pretty good idea. But again, there's so much we just can't know, because galaxies are so much older than the human race. We can't observe them being born. We can't observe these changes happening. So that's something to keep in mind. Everything's a guess, but it's a pretty good guess. Oh, that's pretty cool. Whoa, what just happened? Okay. So that's how we think galaxies form. And so all these objects are falling to the middle of the galaxies. And a lot of them end up doing circles, but a lot of the material actually does end up in the middle of the galaxy. And you don't get a big bright star because there's just way too much mass. The gravity is so big, it pulls it all in to a single point, a singularity, which we call a black hole. We think in the middle of every galaxy is a supermassive black hole. Supermassive meaning way bigger than normal black holes that we've been able to find. But we can't confirm it, and the reason is because black holes are incredibly hard to see. They don't actually produce any light themselves. That's why they're called black holes. But we can see the material that's around them. That material will light up. And so we can get a clue that there's a black hole because the material around it gets hot and it starts to glow. But the black hole itself does not have any light. It's actually, the gravity is so big, it pulls things in faster than the speed of light. So not even light can get out. So how do we know that there's black holes? So this is actually an artist rendition. This is not what they would actually look like. But they're just black spots in space. They're almost impossible to find. But notice this effect. We call this lensing. It kind of messes with the light around it. The objects behind it kind of get twisted and bent around. Because their gravity is so big, they pull the light in weird ways. Can you see the lensing effect over here and over here? These are galaxies. The galaxies are totally fine, but the light, as it passes by these massive objects, it gets squished and twisted and bent. They call it lensing because it's kind of like if you put like a cup on the table and the light does weird things as it goes through, like a glass cup or something. Lensing. Okay. This doesn't work. Let me get out of here. The other thing that we can look for is, here's the animation here, is these objects, stars and other things that we can see, they get thrown. Look at this star right here. Oh, here he goes. And he just gets thrown around. Okay. So we can look at things over time and we can see the way the black hole throws other objects. And then recently, this happened pretty recently, I think it was last year, maybe 2 years ago. Let me move my face again. A A really brilliant scientist, she had this idea of taking all of the telescopes in the whole world and pointing them at one place, and then she runs a mathematical algorithm to figure out so that it's almost like they're acting as one giant telescope. They're each getting different parts of the image, and then she uses a computer to stitch all those images together, and they got this image. This is the first picture taken of a black hole. Again, you can't actually see the black hole, you can just see the stuff around it. But it's very, very dim. And this is a very blurry image. Like, we can't get crystal clear images like this. These are made by computers. You can see the lensing effect around it, and then all the stuff around it in orbit heating up. And this is the best we can do for now. I imagine by the end of your lifetime we'll have much better images of black holes. But this was a huge step forward for science, is getting this picture. And this happened I think it was just like a year and a half ago. Very recent. This is very recent science right here. Pretty exciting stuff. Okay, so we get these galaxies. They're spinning in a spiral, or in a... Oh, that's not what I want to do. There we go. Move me back up here. There we go. And they're spinning. They're rotating. And we have 3 different ways that can happen. We have these elliptical galaxies, spiral galaxies, and then irregular galaxies. Irregular is kind of like the dumpster bin. It's just, if we don't know where to put it, we put it here. We get weird shapes out of it. But these are the 3 main categories of galaxies. And I don't want you to think of it, well, I'll show you a picture. So here's how we kind of classify them. We have ellipticals, and they have a number associated with them. And then we have spiral and spiral barred, and then irregular. And this kind of makes it look like it's a progression, like it starts here and it goes to here and then to here, then to here, and then goes to one of these 2. That's not actually how it is. Each galaxy is its own thing. It's not like this is the life cycle of a galaxy. I mean, as far as we know. But these galaxies are so much older than us that we don't know, does this one turn into that one and then turn into that one? It seems unlikely that would be true. So just so you know, we classify them, put them in this category, but that doesn't mean that one turns into the other. It's just, this is how they are. This is how they are as we can see them. Okay? So first let's talk about spiral galaxies. These are the common kind of galaxies. And we do, so S stands for spiral, and we have A, B, and C. And basically the idea is, how tightly wound are these things? So type A, you don't really see any of these spiral arms super well defined. It's just more of like a cloud. Type B, we start getting a couple really well defined spiral arms where you can see clusters of stars. And then we get to type C, you can just really see very clear spiral. So they're all spiral galaxies, but some of them are more, and you don't need to be able to tell them apart. I don't know if I could tell them apart. But just understand that's what they're talking about. A, B, and C. A is not super well defined. C has very clear, sharp spiral arms. So let's look at some pictures. This is the Sombrero Galaxy. I'm sure you can imagine why they named it that. And you don't see any well-defined spiral arms. It looks like it's just a circle going all the way around. So this one would be an SA. This one is either an SB or an SC. You can see a couple really well-defined spiral arms. Okay. And then this one, you got several really well-defined going spiraling all the way out. This one would probably be an SC. So just to think about different spirals, they're all spiral galaxies, and that's what you need to know. They're all spiral galaxies, but they have different, they just look a little bit different, and so we classify them slightly different. Another thing to keep in mind, we'll talk about stars later next week, but the blue stars burn hotter, and they burn through their fuel a lot faster, so they tend to be younger stars. So when you see lots of blue stars, this is the younger part of the galaxy. And then the red stars, they live a little bit longer. They burn through their fuel slower. They aren't as hot. They don't burn as fast. And so the red ones actually are older, or the red and the orange and the yellow ones. So we've got these yellow ones out here. These are very old stars. These outside of the galaxy. And these are probably actually clusters of stars. So that's the other thing to keep in mind. As it spirals, as this thing spins and rotates, we're actually getting new star formation in the spiral arms, and in these dark areas, you're probably what happened is all the blue ones have already died out, and so you've just got the dimmer, cooler burning stars. So I mean that's more speculation here, but so these are the younger stars. They're going to burn out and die, and then these darker areas, they still have stars there. It's just that those stars are quite a bit older. They're not as bright, and there's fewer of them. Okay, the next type of galaxy is called a spiral barred. So this is similar to the spiral, but you notice it's got a big bar right through the middle. And so that middle area, instead of being a perfect circle, is spread out as a bar. Okay, and again, we also have SBA, B, and C. And this one, you have a few arms. It's more clustered. This one, you have two really well-defined bars, and this one even more obvious. Or spiral arms, sorry. You get the bar and the spiral arms. So again, it's kind of like how tightly wound is it. And then the third type of galaxy is called an elliptical galaxy. Spiral barred and spiral are, some people think of them as the same, but they technically are two different classifications. But the elliptical galaxy, this is a brand new type of galaxy. And this, you might say, oh, this looks like just a spiral galaxy with like an SA, not very well defined arms. But the difference is the spiral galaxies are flat. Okay, they've formed into a disk, whereas these ones are spheres. So it will look like this from every angle. It's going to be a ball from every angle. And keep in mind, this is not one giant star. This is 100 billion little tiny stars all close together, so it makes it look a lot brighter. A lot of the stars that you see in the night sky, you can't really see galaxies. They're too far away. We can only see a couple galaxies like Andromeda. But a lot of the stars that we can see when we zoom in actually turn out to be clusters of stars. So there's something fun there. Notice how there isn't any blue in here. Okay, this thing is not spiraling and rotating. It's more of, this is probably a smaller galaxy is my guess, is how you get these more elliptical galaxies. And the reason I say that is because you're not getting new stars being made. You're not getting any disturbances through the clouds to form new stars. These are all yellow and white stars, older stars. These galaxies tend to be older just in general. And it seems like the stars are just kind of, they're all doing their own orbit in different directions, keeping it a spherical shape rather than flattening it into a disk. And the thing to notice about ellipticals is this is an E0. It's basically a perfect sphere. An ellipse, by the way, is a circle that's kind of squished. Okay, it's a mathematical name for a squished circle. So this one is an E0 because it's not elliptical at all. It's a perfect circle. But this one, it's hard to tell where the boundaries are here, but this one is a little bit more flattened. So it's squished a little bit. And then if they get squished enough, they flatten out into a disk, and we start getting spiral galaxies, which is why we get this classification. So E0 is a perfect circle, and as it gets more and more elliptical, it starts to turn into, lenticular is kind of the transition point, and it starts to turn into a spiral galaxy. It gets flatter and flatter and flatter, and then it's a flat disk. Okay, so that's kind of why we put them next to each other, but it's not like these turn into these. These are different from these. But this is kind of the midway point. This, like, the lenticular couldn't decide which way it wanted to be, so it's, anyway. All right, so that's the classifications, and then we've got this last category, which are the irregulars, and they just don't they don't form circles, they don't form flat disks, they just kind of hang out and make weird shapes. I don't have much to say about them. They're just learn the different types of galaxies. And then here's another thing worth mentioning. These are not galaxies. These are globular clusters. And they're tiny, tiny. They're like elliptical galaxies, but they're quite a bit smaller. Instead of having millions or billions of stars, they might only have a few hundreds or a few thousands. And so here's our galaxy, our Milky Way galaxy. And these are all the globular clusters around it. You can see that they're quite a bit smaller. They're not big enough to be considered their own galaxies. They're kind of part of our galaxy. They're like chunks of our galaxy that got thrown out. And what you'll notice is there aren't really any blue stars in here. These are all very old stars. This is, my astronomy teacher referred to these as retirement homes for stars. Okay, just the red ones that take a long time to burn out, the yellow and white ones that take a lot longer to burn out. So when we stand on Earth and we look, we cannot take a picture of our galaxy. Like, we can classify other galaxies because we can take these pictures of them. But we can't take a picture of our own because we're in the middle of it. And it's very big. We'd have to go outside the galaxy, turn around and take a picture and send that picture back. And we just don't have technology to do that. And the project would take, I mean, our galaxy is several light years across, so light can take, I think it was like 500 light years. Is that what it said? 50,000 light years across. Okay. 50,000 light years. So even if we did take that picture, if we got a satellite up here and took a picture of our galaxy, it would take 50,000 years for the signal, because we send it as light. Radio waves are a form of light back to Earth. It would take 50,000 years for the image to go from the camera back to the person who took the picture. So again, we just don't have time to take a picture of our own galaxy. So we have to make guesses of what our galaxy looks like based off of the clues we get. So this is a long exposure of the night sky, and this is actually one of the spiral arms of our galaxy. So one of these spiral arms out here. And scientists have looked at it. They've actually tried to find the supermassive black hole in the middle of it. And they have some good evidence that there probably is a supermassive black hole in the middle of our galaxy, which is why we think that there's supermassive black holes in the middle of all galaxies, but we don't know for sure. And this is kind of just plotting the stars on a map. This is what we think our galaxy, the Milky Way, this is what we think it looks like. And this right here is where our star is. So we think so if you have this in here, oh, I wrote it on here. Spiral bar, I was going to ask you, what kind of galaxy is this? Based off of the image. But then I forgot I typed it in over here. This is a spiral barred galaxy. It's a SBBC. That should be a lowercase b. Because we're not sure if this is a B or a C type spiral bar. So they call it SBBC because it's somewhere in between the two. And if we could take a picture of it and actually see it for sure, we would have a much better idea of what kind of galaxy it is. So that's why there's some uncertainty here. All right, so that's the whole presentation. Not a very long, well, it actually turned out to be kind of long.